Hey guys, in this video we're going to discuss finding the zeros of a function, which is something we often do when we are working with graphical analysis or sometimes just algebraically. We're talking about finding the zeros of a function, but zeros, I do want to bring up this word very quickly because often you'll find that you'll be asked to use another word. Instead of zeros, you could say x-intercepts, or you could call them roots. Okay, or you call them solutions, but today we're going to be calling them zeros, and because we're going to be using the digit zero. But anyways, let's talk about this. This is the definition right there, okay? So the zeros of a function, by definition, are all of the x values for which f of x is equal to 0. In other words, they're all the x values that when we plug them into this function right here, the function value actually goes to 0. And another way to say this is, they're all of the x values, like this, I guess, for which y, or the function value, is necessarily 0. You can think of this as being y. Okay. So I think the best thing to do is start by looking at this in terms of graphical interpretation. But let's say we had some function that was drawn. We'll make it look like a cubic. Okay. So a little sideways s. But if we had this cubic function here and it increased, we can call this g of x. Why not? G of x increases, decreases, then increases. The fact of the matter is this: when we're finding zeros, what we're really concerning ourselves with are these x values, that when we plug them in, we got y values of 0. So as you heard me say already, this is kind of like saying, like x-intercepts, because here's one thing we know about the x-axis. Every single point on the x-axis is unique in the fact that whatever the x value is, its y value is equal to 0. So if we wanted to find necessarily where a function intercepted the x-axis, we could insert 0 in for a function value and solve for x. And this is just a common method we use to find x-intercepts in the first place. So when asked to find the zeros of a function algebraically, we can use the same property we used when we were finding y-intercepts. Okay? I think the best thing to do here is look at a couple of functions algebraically that we've been asked to find the zeros for, starting with this example a, but we'll work with what we're going to call f of x. And we'll let f of x equal, how about 3x squared? We'll do a quadratic. It'll be nice to have an a value other than 1. But let's call it this, okay? Now, finding the zeros of this, of course, again, what we're really looking for graphically are the x values for which we're at a height of 0 on our graph, okay? But algebraically, we're saying, okay, I want to know what are the x values that would cause necessarily this value right here to be 0. So the best thing to do here is go ahead and let's set f of x equal to 0. And what we'll do is we'll just back solve for x here. Okay, so set y equal to 0 or f of x equal to 0, so back solve for x. Since this is a quadratic and it's a trinomial, we can go ahead and try to factor this, and it's possible we can't factor this, and if we couldn't, we would have to rely upon, specifically in this instance, the quadratic formula, which I know everybody loves. But let's go ahead and check this out. Now, since we have an a value that is not 1, we can't just, if this is factorable, we cannot just load this up with like an x here and an x here. Although that when we do FOIL this out, we would get x squared, but we need to get 3x squared. So really what we need are some factors of 3, and we're very limited in this instance. We're just going to have to go with 3 and 1 since it's prime, and that's fine. So 3 and 1. But I want you to know at this point, we are guaranteed when we FOIL this out, just to make sure we get back to where we started, to get our 3x squared back. Okay? So the next thing we're going to try to get here, we're going to fill in these last two spots. And what we want to try and get here is a negative 10. So the best thing to do sometimes is just write out the factors of negative 10. We say, okay, so negative 10 and 1. We go positive 10, negative 1. We could go 2 and negative 5. We can also go negative 2 and positive 5. The thing here is, when you have a leading coefficient with an a, it's not a value of 1. We just have to do a little bit of guess and check, okay? So I'm going to start with this. How about we go with, sorry, I'm going to do a little rearranging here, if I can. Well, I guess I disappeared my tools there. Anyways, we'll go ahead and put in, say, I don't know, 2 and negative 5. Now, I can't make a guarantee here, but in my experience, I found that when you have to do this guess and check method, the best thing to do is to start with factors that are very near to each other in terms of distance. And negative 10 and 1 are further apart than 2 and negative 5. So we'll go ahead and do this. We'll say plus 2, negative 5. And now we're guaranteed here with these last two terms to get our minus 10. The only thing we have left to check here is to make sure we get this positive 1x in the middle. And so how we do that is we necessarily check the outer and the inner multiplications, okay? So you'll notice here we get 3x times negative 5 is negative 15x. That would give us negative 15x. And the inner multiplication would give us positive 2x. So now that's a difference of negative 13, which is, in terms of magnitude, way off of being a 1 here. So I don't have a problem with 2 and 5. Maybe perhaps we switch them around. So we're going to do a little working backwards here and just undo this here. Instead of positive 2 and negative 5, how's about we go negative 5 and positive 2 and just see what happens. So this time we do our outer and inner multiplications. You see here we get positive 3x times 2 is 6x. We'd be adding that to negative 5 times x, which is minus 5x. And would you look at that? We have our 1x, which is what we wanted. So now we've got our plus 1x minus 10. This would get us back to where we started. Okay? And so our effort to factor this in the first place was simply because we wanted to solve this equation. And since it was second degree, we'll factor it. And then we'll set each factor equal to 0. So we say 3x minus 5 is equal to 0. Or x plus 2 was equal to 0, or they both were. But solving both of these equations, we yield the fact that it is the case that x would, adding 5 and dividing by 3 here, be positive 5/3. And in this instance, x would be equal to negative 2. And so the neat thing about this is when finding the zeros of a function, you're really finding what we also call the solutions of a function. But the x values that cause y to be 0, we can just plug these x values back into the original equation and determine that we would necessarily end up with a y value of 0. For the sake of time, however, I'm going to go ahead and move on to a couple more examples. Let's go ahead and look at example B here. I've written one out. We'll call this one g of x. Okay, in g of x, we're going to have radical, and let's go 10 minus x squared. This is something we deal with often, sometimes, but we say, okay, finding the zeros, let's go ahead and set g, our function value, equal to 0, and we'll just back solve here. So algebraic sleight of hand, since we have a radical here, we'll go ahead and square both sides. And of course, squaring both sides is not going to affect the left side. It'll affect the right. We have 10 minus x squared. Go ahead and subtract 10 from both sides. And I'm going to use our reflexive property here. We've got negative x equal to negative 10 now. I just switched our sides when I subtracted that 10. But since this is negative and this is negative right here, we'll go ahead and multiply both sides by negative 1 and just yield x squared equals positive 10. And so what we find out is this. X squared, to undo this, we'll square root. And since this is a second degree, we really should have two solutions. So remember, we're not just going to say it's the square root of 10, but we're going to say plus or minus the square root of 10. Okay? And this one's actually really easy to check. I do want to check this one. But if we say put in a positive square root of 10 for this x squared here. So inside here we'd have 10 square root of 10 squared. That squared and that square root are going to cancel out and leave 10. And when you have 10 minus 10 inside the radicand, of course that's 0, and the square root of 0 is 0. So we get 0 equals 0. Kind of nice. Okay. And then one more example real quick. We say C. C is, we'll call this h of t. Now this is a unique example. If you're watching this and you're taking notes, I would highly recommend that you write this one down. But this is what we call a rational function. Okay. And it's a rational function because, you know, it's a ratio. It's a comparison of the top to the bottom. But the fact of the matter is it kind of calls on our knowledge of ratios or fractions when we set this equal to 0. Of course, we're going to still set this equal to 0 and go back and try to solve this equation. Well, we will. But the fact of the matter is this thing on the right here is a ratio, and if you think about this, if it's equal to 0, if I said, you know, some fraction a over b was equal to nothing, I say, well, which one of these values would necessarily have to be equal to 0, the a or the b? And of course, here's what we know. If b was equal to 0, we'd have something that's undefined. So in other words, the only way that the value of a ratio or fraction can be 0 is if the numerator itself was equal to 0. So the nice thing about these problems is when you set a rational function equal to 0, really all we're concerned about is this numerator. So if we set this numerator equal to 0, we say 2t minus 3 is 0, and add 3 to both sides. Now we have, it follows that we have 2t is 3. Now dividing both sides by 2, we just end up with t as being 3/2. So this function itself would actually have only one 0. And it'd be worth the time to go back and actually, if you have a graphing calculator, plug these functions into a graphing calculator and see that those are the x values for which their graphs, or the functions of their graphs, or the graphs of their functions, would necessarily intersect the x-axis.